In this video, I'm going to be covering the notes for Unit 4, Section 2, focused on ionic bonds. There will be four parts to this presentation. First, we'll go through a quick refresher on ions, talk about what ions are and how we classify them. Next, we'll talk about how to determine a charge on an ion, so how strongly that ion pulls on another. Third, we'll talk about how to name ionic compounds. And fourth, we'll talk about what their formulas are. How many of each ion do we need to form a stable ionic bond? So first things first, a quick refresher on ions. Ions, remember that these are formed whenever an atom changes how many valence electrons it has, those outermost electrons. Now, with ions, we kind of have to think backwards. If we remember that electrons are negative, if we lose valence electrons, your ion will become positive because you're losing those negative charges. Alternatively, if your atom gains valence electrons, it's going to become negative because it's gaining something negative, an electron. Take, for instance, this atom of sodium here. You can see the Bohr model on screen. This atom is not quite stable yet. It has this single electron in its valence shell. And remember that atoms, they are stable when they have a full outer shell. So this outermost electron, it's most likely going to be lost. And when we lose that outermost electron, your charge, as shown in the bottom right, will become positive because you lost a negative. So when you have that full outer shell because you lost a valence electron, the atom, or now ion, has a positive one charge because you lost the negative. On the flip side, if we look at an example of, say, fluorine, you can see fluorine has an empty spot in its outermost shell. Let's say fluorine gains an electron in its valence shell. By gaining a negative electron, the charge will become negative. It gained one negative charge, so the overall charge is -1. And this applies for multiple electrons as well, although we'll see that in a later slide. So positive ions, what do we call these? Well, atoms which lose electrons and become positively charged, we call these cations. This comes from the terminology from batteries, where the cathode is the positive end of a battery or circuit. So if I look at something like lithium, it's going to lose this single outer electron, this single valence electron, and become +1. Magnesium is going to lose these two valence electrons and become positively 2 charged. And aluminum is going to lose these 3 outer electrons and become positively 3 charged. These are all considered cations. They all have a positive charge. On the other end of things are negative ions. We call it when atoms gain electrons and become negatively charged, they have the name anions. This comes again from batteries, where the term anode comes from the negative end of a battery or circuit. So fluorine, as mentioned, it has one spot open in its Bohr model. It's going to gain 1 electron and become -1. Oxygen, 2 spots, one here and one here. It's going to be -2 charged when it gains those 2 electrons. And nitrogen with 3 spots, 1, 2, 3, will gain 3 electrons and become -3 charged. Because these are all gaining electrons and having a negative charge, these are all types of anions. Now let's talk about how to determine ionic charge. It's pretty much as simple as what we just discussed, but we really have to fold back in Lewis dot structures. If we look at the periodic table, it's pretty easy to tell what the Lewis dot structure for an atom will be. Remember that these Lewis dot structures show that outermost organization of electrons. They show the valence shell. And the process for drawing them is simply count from the left of the periodic table, but only look at the S and P blocks, as highlighted here in orange. We're going to skip the transition metals or D block elements for now. So as we count over, you can see we add 1 electron each time. And from these Lewis dot structures, it's fairly easy to tell what the charge will be. But again, this only works for the S and P block elements. We can't use these simple rules for the D block elements. So how do we tell the charge? Well, it's pretty simple. At least for the first 3 rows of the periodic table, the element will either gain or lose electrons so that that outermost shell is full. It either wants to fill up that outer shell or lose what it has to go down to the previous shell. So potassium, for instance, it has 1 electron. It's a lot closer to having none than it is to having a full 8. So potassium, because it's closer to 0 electrons, it's probably going to lose that single electron, and it will gain a +1 charge because it lost an electron, forming a cation. Oxygen, that's much closer to 8 electrons. It has 6. It only needs 2 more to be full, so it can either lose 6 or gain 2. It's a lot closer to 8. It's going to gain 2 electrons. And by gaining 2 electrons, oxygen would have a -2 charge. Calcium, with 2 electrons in its valence shell, it's pretty close to being empty. It's closer to 0 than it is to 8. So because it's closer to 0, it's probably going to lose its 2 electrons and become positively charged, forming a +2 cation. And fluorine, as mentioned many times at this point, fluorine is missing 1 electron to have a full shell. It's obviously closer to 8 than it is to 0. It's going to gain 1 electron and have a -1 charge. So if we take a look at the periodic table, and we remember that, at least for the S and P block elements, every element in a column, those groups on the periodic table, they have the same outer shell configuration, except for helium. That's one of our oddball elements. Because they have the same configuration, they're going to have the same charge a majority of the time. So again, if we just look at the S and P block elements, you can see that the first column all have +1 charges typically. The second column all have +2. If we skip the center, we can see that at least for the first first 3 rows of the periodic table, we can see these elements are a +3. And honestly, that is true of many of the elements below as well. These will also typically form +3 charges. Notice though that our elements with 4 electrons, I'll go back a little bit, these elements here, are elements with 4 electrons. It is not clear whether they would lose the 4 they have or gain 4 more. What that means in terms of ions, this column, starting with carbon, doesn't really form ions that easily. They don't lose 4, they don't gain 4, they just don't form ionic bonds. Going further, we see a pattern kind of in the opposite direction. This column has a -3 charge, this column is a -2, this column is a -1, and our noble gases, because they're already full with valence electrons, they also really don't form any kind of charge. You can annotate your periodic table with the charge above these columns as a reminder. Now, I skipped the transition block, those D block elements, because they're a bit odd. Most can have multiple charges. Those transition elements, you don't have to memorize these. You could memorize the important ones, but I've given you a set on the resource chart. These are yours to just refer to. You don't have to memorize the rules. I might cover it in a later lesson. Just know that some of these, like say lead, can have multiple charges, whereas others, like manganese, they typically only have 1 charge. It is a bit more complicated than this, but for us, that's good enough for now. Also, know that some ions exist as groups of atoms, and we call these polyatomic ions. This chart is on your resource page, and it just lists the groups of atoms that act like an ion. So, for instance, we can see right up here nitrate, NO3 -1. That means 1 nitrogen and 3 oxygens paired together. That acts like an anion with a -1 charge, and we call that nitrate. There are some patterns on here that we'll go through in a later lesson. Know, though, that these polyatomic ions, they still act as single pieces or single elements when it comes to ionic bonding. For instance, if we have sodium that has a +1 charge, and one of our polyatomics, sulfate, that has a -2 charge, we still treat the sodiums as individual pieces, and we treat the sulfate as an individual piece, sort of like the solid sphere atomic model. It makes our lives a lot easier. Now, when it comes to naming ionic compounds, there's a few relatively simple rules. When it comes to simple ionic compounds, 1 element from the S block and 1 element from the P block, the rule is we always name the cation or positive first, and it keeps its name. The anion always comes second, and it changes the ending to "ide." So for sodium and chlorine, sodium with a +1, chlorine with a -1, sodium comes first and stays the same, chlorine comes second and changes to chloride, forming sodium chloride. Beryllium and phosphorus, same thing. Beryllium comes first because it's positive, phosphorus comes second because it's negative. Instead of beryllium phosphorus, we call it beryllium phosphide. and magnesium and bromine. Instead of saying magnesium and bromine, we say magnesium bromide, the magnesium being positive and the bromine being negative. So simple ionic compounds, pretty simple rule. Notice the amount of each ion, as shown here with these subscripts, doesn't actually change the name. It will in terms of transition metals, but for our simple ionic compounds, doesn't matter. We're going to skip this question, but go ahead and if you'd like, pause the video now and try to find the names of these two ionic compounds. On the left, you'll see calcium, the positive, followed by nitrogen, the negative, forming calcium nitride, and beryllium, the positive, followed by oxygen, the negative, forming beryllium oxide. Now, when it comes to naming ionic compounds with polyatomic ions, the rule's even simpler. Cations first, anions second, and every polyatomic ion just keeps its name. This goes on top of the rules we just talked about. So sodium, Na, and sulfate, SO4, just form sodium sulfate. Potassium, the positive K, and chlorate, the negative ClO3, forms potassium chlorate. And ammonium and sulfur, the positive ammonium comes first and keeps its name, the polyatomic. And sulfur, because it's second and because it's a simple anion, it does change to ide. If it was a polyatomic, it would not. And that is how you name ionic compounds. We will talk about transition metal naming in just a little bit, but we have to talk about formulas first. So when it comes to ionic formulas, the main rule is that the overall ionic formula has to have a charge that is 0. For instance, if we have sodium with a +1 charge and oxygen with a -2, this charge would not be balanced. Right now, there is more negative than positive, so we have an overall negative charge. To fix this, we could add another sodium, and we'll see that now our overall charge, 2 positives 1s and 1 negative 2, the overall charge is now 0. In other words, the formula for this compound would be Na2, showing there's 2 Na atoms or 2 Na ions, and O, notice I don't put a 1 here. We don't put 1s if there's one of a compound. We, as chemists, we oftentimes omit 1s. So Na2O, also notice there's no charges in the actual formula. The charges tell us the formula by doing our math shown here on the right, but we don't have to indicate charge in the formula. Now there is a quick trick of finding the ionic formula, and that is to simply switch the charges. Essentially, the charge on the cation becomes the amount of the anion, and the charge on the anion becomes the amount of the cation. Ca +2, P -3. The charges will switch their positions and show that if we have Ca +2 and P -3, we're going to need 2 phosphoruses and 3 calciums. And this would work because right here we'd have 3 +2s, giving us a total of +6, and right here we'd have 2 -3s, giving us a total of -6. Now this quick trick does have an exception, and that is that the amounts of each ion must be the lowest common factor. So if we look at, say, magnesium and oxygen, if we switch these charges, it'll suggest that it's Mg2O2. That is not the case, however. It's actually just MgO. We could divide each of these by 2 to get the lowest common factor, or just note from the beginning that Mg and O are already neutral as is with one of each. So you only need one of each to form your ionic compound. The same is true for polyatomic ions, except if we need multiple, we have to use parentheses to keep that ion together. For instance, if we have calcium with a +2, phosphorus with a -3, right now we have more negative than positive. We'll add another calcium. Now we have more positive than negative. We'll add another negative. Now we again have more negative than positive. I'll add another positive, and now we've reached a neutral ratio. You could have also just done the switch trick to see that we needed 2 phosphates from the calcium's charge and 3 calciums from the phosphate's charge. Now, how do we write this formula? Well, the Ca is simple. Because it's a single element, just say Ca with 3, showing there's 3 calciums. The phosphate, though, because we have 2 of them, we have to put parentheses around the phosphate to essentially say we have 2 of the entire group, the entire polyatomic ion. You don't have to put these parentheses if there's only one of the polyatomic ion, but if there's ever multiple, you do have to put parentheses. Now with transition metal ions, we do have a little bit more work to do. Luckily, all transition metals are cations, so they will always come first. However, because they can have multiple charges, we oftentimes need to specify their charge. The rule is we follow their name, followed by Roman numerals in parentheses to state their charge. And this is only necessary if the metal has multiple charges. For instance, with this lead oxide, because lead can have two possible charges, we actually have to do a little bit of backtracking to find out which charge we're even talking about. Oxygen we know has a -2 charge. So if we check the total negative, we'll see that it's -4 in total. So the only thing that would work is that this lead is +4 to balance it out. Therefore, we know this is lead 4 oxide, one of those options for lead. If we look at, say, something like iron and nitride, iron has two possible charge states, 2 and 3. If we look at nitrogens, -3, we can see the only thing that works here is a +3 to balance it out. So this is iron 3 nitride. For copper and sulfate, copper has two options, a +1 or a +2. If we look at sulfate, sulfate has a -2. So the only thing that works here, again, is copper having a +2 charge to balance. So we have copper 2 sulfate. And do be careful, because every once in a while, there's an element that only has one possible charge. Silver, you'll see, only really forms a +1 charge pretty often. So silver oxide, you actually don't have to write silver 1 oxide, because there's only one option. And so if you're going from, say, name to formula, it's pretty easy. The number tells you, the Roman numeral tells you the charge. If you're going from formula to name, you'll have to do a little bit of detective work, figure out the charge, the total charge of the anions, and balance it out with the possible charge of the cations, that transition metal. And that is it for the Unit 4, Section 2 notes on ionic bonding.